this lesson, we'll discuss the fundamentals of quantile regression. We start the discussion with the shortcomings of the typical linear regression model like OLS. Then we provide the background of the quantile regression model. First, we discuss the basic properties of quantiles. Then we discuss the unconditional univariate quantiles. Then we compare conditional mean with conditional quantiles. Then we start the analysis with a simple bivariate problem. We also discuss a simple example and introduce a p-variable problem. Then we start with a dummy variable example in the context of quantile regression. Next, we add nominal variables as regressors. Lastly, we also discuss quantitative regressors in the quantile regression model. In this video, we'll start the discussion with some of the shortcomings of classical linear regression model. We have already discussed the linear regression model. We have also discussed its ordinary least square minimization scheme, where we minimize the summation of squares of residuals or regression errors. Let us start with the shortcomings of this LRM or classical linear regression model. It focuses on the conditional mean or that average or that yi bar of the response variable. So ultimately you try to estimate the conditional mean without accounting for the full conditional distributional properties of the response variable. So your response variable yi may have a full spectrum of distribution. However, this linear regression model focuses on the mean, the average value of this response variable. In contrast, if you look at quantile regression model, it facilitates the analysis of conditional distributional properties of response variables. So with quantile regression model, not only you are interested in the median value, which is corresponding to mean, although different. So you're looking at median, but also you're looking at other quantiles, for example, 5 percentile, 10 percentile. So it lets you or gives you the flexibility to estimate the response variable across different quantiles. It is unlike the linear regression model, which is focused totally on the mean. In the scheme that is followed by linear regression model, the means scheme has certain problems in real life data. For example, if whether you're looking at financial market data or any kind of data, you have the following problems. First, data tends to be heteroscedastic. The model assumes homoscedasticity, that means variation of the error term, the sigma square, the variance remains constant. And it also assumes the data is not skewed, it is symmetric, and the kurtosis, which is similar to a normal distribution, a kurtosis of 3, which is similar to normal distribution. So these are some of the assumptions of classical linear regression model. However, in real life business scenarios, the data is not only heteroscedastic, it's sometimes skewed, and also it has kurtosis. Kurtosis means excess peakness and fat tails. So if your data has fatter tails as compared to normal distribution and excess peaks, like this is a higher peak and fatter tails as compared to the normal distribution, the tails are fatter and peak. Also, different shapes of the contributional distribution of response variables. So often there is a shape shifting due to covariates. So because of the nature of covariates or the independent variables, the shape may not be as required for the linear regression model. As theoretically required shapes may not be there. It may change. It may be conditional. Also, another problem is the presence of outlier. So when there is presence of outlier, the mean is affected, not the median, and other quantiles are not affected, but mean is affected. So all in all, what we infer that application of linear regression model for practical scenarios is often fraught with challenges in estimation. And to circumvent and avoid those challenges, quantile regression model with its estimation of quantiles rather than mean presents a very good and clean model. In this video, we'll briefly introduce the mechanics of quantile regression model and its background and the motivation. Recall we said that classical regression model focuses on the conditional mean. So if you are looking at a regression of this kind, y1 equal to beta 1 plus beta 2x plus error term, if it is estimated based on classical regression model with the OLS scheme, ordinary least square scheme, you would estimate a value of y, let's call it y hat, which is nothing but expected value of y given x, and that expected value is the expected mean. We call it conditional mean because it is conditional to the values of x. In contrast, quantile regression allows us to study the full conditional distribution of y at different locations. For example, the different locations of y may be 5 percentile, maybe 10 percentile, or 25 percentile, which you call as Q1, or median, which is 50 percentile. may have different behaviors. For example, the differential effect of covariate, that is x, at different quantiles may be different. For example, think if you are studying the income versus expenditure of a family, maybe expenditure on food, surely the families at a lower income may have different food expenditure habits. As a percentage of their income, the food expenditure would be higher as compared to families with very high income. Their food expenditures would be of different nature, and as a fraction of their income may be lower. So there's a different behavior when you study the full spectrum of the dependent variable across its conditional quantiles. And also, if there is a problem of heteroscedasty, that means variance of error term is not constant, or there is a complex shape shift. By shape shift, we mean the impact of covariate on different y is different. For example, if you study the impact of y at lower quantiles of y, the impact of x at lower quantiles versus impact of x on higher quantiles, that may be different. So the shape or the relationship may change over the conditional distribution of y. That is also QRM is fully capable of capturing that. Now, mathematically, if you start with thinking in terms of univariate distributions like y, mean and medians are like centers of the data. And they are often used to define whether the distribution is skewed or not. So when you think of OLS, essentially what you are doing, the mean of the center is the place where you are minimizing from the center the sum of error squares. So here the center is like expected value C, which is the expected value of y. So any deviation, let's consider that as error. So any deviation y minus c is your error ei. So the expected value of this ei square, or typically this this minimization scheme where you are trying to minimize this expectation of square, you will get the mean. So minimizing the deviation square results in a scheme that gives you the mean, or when we transpose it or sort of translate it to the conditional distribution, we get OLS. But in univariate distributions, it is simply the scheme where you minimize the error. Error from what? Error from the center. If you minimize the squares or compute the expectations of these squares, we get the mean. Median is nothing but very similar scheme, but we are not minimizing the squares, we are minimizing the absolute deviation. So if you minimize the absolute sum of deviations or expected value of deviations from the center, which is also the summation of these deviations, you get median. So if I show you in terms of diagram, if this is your univariate distribution of a value and you have a some center C from which deviations are minimized, absolute deviations are minimized, then you get the median. But if you minimize the square deviations, you get mean. So this would be the mean when you are minimizing the square deviations. This would be the median if you are minimizing the absolute deviation distances. So this is the typical scheme to understand what is the mechanics and mathematics behind the quantile regression model as compared to the typical linear regression, which we call as ordinary least square model. So to summarize, in this video, we saw the mechanics behind the QRM model, how it is obtained. It tries to obtain one quantile, which is median. Median is one example of the conditional quantile. There are many such quantiles as we'll see, but median, which is the 50 percentile, is nothing but the center when deviations from the center are minimized in absolute terms. In this video, we'll briefly introduce the concept of quantiles. Simply put, if a student performs better than tau proportion and worse than 1 minus tau proportion of students giving a particular exam, then he or she is considered to have obtained tauth quantile marks. So if it is above 99% and below 1%, then you will call it 99th percentile. This is also expressed in terms of quantiles. Now, any random variable can be characterized by its distribution. So all the variables, they have their distributions, and you also express in the form of cumulative distribution function fy, where fy equal to probability of y less than y. So here a cumulative function is nothing but the probability of y being greater than the remaining y's. So all the y's from which it is greater than the total probability of those y's is fy. For example, let's suppose in a given distribution, a particular value of y is greater than 99% of y's. So the distribution of y is such that 99% values are less than this y or less than equal to, it won't matter much. So then in that case, the probability that y's are less than equal to y is fy, which is equal to 0.99. This is the cumulative probability of that particular value y. Now, in this backdrop, quantile function can be defined for a particular quantile tau as q tau, where q tau is inverse of probability, cumulative probability function. So when it is applied on tau, you get a value of y. That means, a simple example, let's suppose we said that y is greater than 99% of the values of distribution of y, which means the cumulative probability of y being all the y's being less than y is 99%. That means 99% of y's are less than this. So if we apply, this is also called cumulative function, which is expressed as fy. Now suppose the inverse of fy. So if we apply inverse of fy on this quantile value 0.99, or what we are calling as 99 percentile, then we should get a value of y. So this quantile function is nothing but inverse of, if I apply inverse of probability density sort of inverse, which gives you the value of y. So to summarize, in this video, we described how to understand the quantiles and what is a quantile function, which we said is sort of inverse of cumulative probability function. In this video, we'll understand some very basic properties of quantiles that are useful in their applications. One very important property of quantile is monotone equivariance. To start theoretically, any monotone transformation h, such as log or exponential or any similar function of a random variable, one can still obtain the quantiles by applying the same transformation to the quantile function. What do we mean by this? In simple terms, let's say if q is the pth quantile of y, that means if I find pth quantile of y, that is q, then h of q is the pth quantile of h of y. Let's take an example of log. Suppose in a sample data, 20th percentile is 4300 in a given distribution of y. Y is so distributed that 4300 is 20th percentile. And if the data is log transformed, if I transform the data in a logarithmic form, then for the transformed data, the 20th percentile would be log of 4300. So for that log transformed data, 20th percentile would be log of 4300, which is 8.37. So this is monotone equivariance property of quantiles. There is another very useful property of quantile that is often employed, is that these quantiles are insensitive to the influence of outliers. Suppose in a given sample of data x1 to xn with a sample median m, if I transform any value which is lower than median or any value to the higher than median, suppose this value, I by mistake replace this with a very low value, or by mistake a value high with a very high value, anything what is happening on the lower side or higher side, as long as the values are not switching the sides, the median will remain unchanged. So such modifications will not have any effect on the sample median. And similarly, if you look at any quantile also, suppose 25th percentile I'm looking, or 75th percentile, but median is also 50th percentile. So as long as anything is changing here or on the positive side of this 25th percentile, its value will not change. It will remain unaffected. However, the same does not hold for mean. So in this video, we discussed some very basic properties of quantiles. We discussed that they are insensitive to the influence of outliers, and they also follow what we call as monotone equivariance. In this video, we'll fix the ideas behind quantile regression with the help of unconditional univariate quantiles. Let's start. In a very simple terms, univariate quantiles are defined as location of distribution such that the cumulative probability corresponding to a quantile is theta. For example, suppose a particular y defines theta quantile in a distribution of values in y. So y contains a set of value where theta quantile is y. Now, if I accumulate the probability of all the y values that are less than equal to y, I'll get a cumulative probability theta, and therefore that is the reason why y is theta quantile. If I define a cumulative probability function or CDF such that fy, where fy is nothing but probability of all the y's, cumulative probability of all the y's less than, taking less than value of y, less than equal to y, it's theta. So our typical cumulative CDF is defined as this, which is equal to theta. Here we can define quantile function q theta as inverse of CDF. That means if I apply this q on theta, or in other words, inverse of theta, we'll get that y value where theta is from 0 to 1. Here CDF is typically increasing and continuous. Let's try to visualize that. So I have plotted CDF here where on x-axis we have set of y values. For example, suppose 25 percentile is 12.2. So 12.2 maps to 25 percentile, while 17.7 maps to 50th percentile, and 23.3 maps to 75th quantile or percentile. So this is our typical CDF, which is rising. Now suppose I want to map quantile with quantile function. So on x-axis I have quantiles like 0, 0.2, 0.4 and so on. Now recall, if I want to map 25 percentile, I apply function q theta, and recall here 12.2 was the 25th percentile. So the quantile function applied on the 0.5 will give me 12.2. Similarly, quantile function applied on 0.5 will give me 17.7, and quantile function applied on 0.75 will give me 23.3. And this is how we'll map quantiles to their quantile function. So now let us fix the mathematical definitions behind quantile. Recall earlier we defined median as a problem of minimizing, we are minimizing the expectation of a particular absolute residuals from the center. So for example, if y are set of values and c was that centroid median, the errors or deviations from this median centroid could be obtained as this simple problem of minimizing the expectations of these errors or residuals. Let's call them yi's. Or it can also be called mu I or yi, which is the deviation from center of y values. Slightly elaborating this concept now, quantiles are also can be thought of as a solution to this minimization problem of this sort. This is nothing but weighted absolute sum of deviations, as we'll see. This is the deviations. Some check function, that loss function or check function rho theta is applied on them, and that expectation is minimized. And we'll see later this loss function or check function is nothing but weighted absolute sum of deviations. The idea here is that quantiles act as a specific centers of distribution. For example, median was a kind of center of distribution where 50% values were low and 50% were above. Similarly, 25th percentile or quantile can be thought of as position where 1/4 of the values are less than this and remaining 3/4 are above. So we define our typical loss function rho theta y as this: theta into 1 minus indicator function into y, where indicator function takes a value of 1 when y is less than equal to 0 and 0 when it is positive. Effectively, what is happening, you can think of y, which are the deviations from the center. Some value would be positive and some value would be negative. Now I can expand this like this, where if the in this particular form, if y values are greater than 0, then this will be 0 and you'll have only theta. This value will be 1. So you'll have theta into y, where theta is positive, y is positive. So if y is less than 0, then this value will be 0, this value will be 1, and this will be theta minus 1. So theta minus 1, which will be negative because theta is from 0 to 1, will be multiplied by y, which is also negative. I'll get a positive value. So essentially what is happening, we are multiplying the magnitude of y or weighing the magnitude of y with 1 minus theta for negative deviations of y, and weighing it with theta for positive values of y. So effectively you can say we are multiplying magnitude of y with 1 minus theta wherever y's are less than 0, and if they are greater than 0, we are weighing it with theta. And typically this problem can be expressed with this formula, where this is your loss function or check function applied on y. And solution to the minimization problem, the solution would be quantile. So quantile can be defined as solution to this kind of minimization problem, where we are minimizing the expectation of this loss function defined like this. So let's concretize our understanding. We defined a check function or loss function like this, where deviations mu I or yi's are multiplied by tau minus indicator function, which takes a value of 1 when mu is less than 0 and 0 otherwise. Effectively, you are multiplying the absolute values of y with 1 minus tau or theta for negative values of y, and tau with positive values of y, which is nothing but this minimization problem. If you think of it, this minimization problem where loss function or check function on yi minus c is applied, where yi takes a set of values, and here you will have error terms or deviations. These mu i's are deviations, that is for each yi minus c you'll get some deviation mu I, which will be further fed into this check function, and the minimization problem will give us that centroid or quantile. So effectively what this check function would do, that for all the negative side residuals will be multiplied with mu I would be tau minus 1 and positive residuals mu I would be tau. So effectively it is like saying multiplying mod with 1 minus tau for mu less than 0 and multiplying error residual with tau for mu greater than 0. Recall, if it is half, then you'll get tau as a median. So to summarize, in this video, we tried to formulate our quantile as solutions to minimizing a particular loss function, which is a weighted value of deviations. We were multiplying or weighing the deviations with certain quantiles, and the solution to that problem is the quantile itself. For now, we understood in the form of unconditional univariate distributions. In this video, we'll see a simple proof of quantile regression problem where we'll see how univariate quantiles can be presented as a solution to the minimization problem where we minimize the expectations or summation of absolute residuals. Recall the check loss function that we have discussed is minimization of expectation of this check loss function rho theta, where y we can take as univariate. We can extend this logic to conditional response functions such as a regression model, but think of y as a univariate distributed variable and see some kind of center. Now, for simplicity, rather than check loss, we look at a specific position which is median. And for median, this check loss function minimization becomes this expression. Here y is a continuous random variable and we are trying to minimize the expected value or absolute sum of deviations from a given center C. Now C is some kind of center and we will try to show that this center is indeed median when we minimize this kind of absolute residuals. You can think of y as distributed, some kind of univariate distribution, and fy is the probability density function. So this expectation can be expressed in the form of integral, assuming that y is a continuous random variable. So we can express it like this, where y is a sort of, you can think of a real number. Now this is mod. So this is, we need to make this differentiable over the full range. So without any loss of generalization, we can simplify, we can break it down into two pieces. So for example, this is the first piece where y is less than c. You can think it of as minus infinite to c. And here in the second part, y is greater than c, which is c to infinite. Now we can open the mod and make this function easily differentiable. So from minus infinite to c, we can open this mod by writing c minus y and this as y minus c. So now we have two differentiable functions. We'll look at them piece by piece. We'll first solve this one and then try to apply the same logic to work out the solution for the second term. Now, this kind of function is sort of convex in the sense that it appears like this. So when if you want to minimize this kind of function and you take differential, you'll obtain minima. So when you set del by del differential slope here, you'll get minima because the nature of shape is convex. See, if you recall, the mod appears to be something like, so you'll obtain minima, not maxima. Let's start with this. So we want to differentiate this function with respect to c. We'll set the differential to 0 and find the solution. Now this requires application of Leibniz integral rule for differentiation under the integral side. So there is an integral side. We are looking at first term first. So let's look at this Leibniz rule and try to match term by term basis. Here the limit is from minus infinite to c and we are differentiating with respect to c. First and foremost, look at this expression. Here t is parallel to y. So you can think of this dt as dy. And this function fy, which is your probability density function, this entire combination. Now, please notice, because lower limit here is a, which is infinite. Now, this infinite is constant, unlike a, which is some function of x. And x here you can think of c. So c itself is c and the function which is bx upper limit, that is also c. So c bx is also c and c is anyway there. So we take the differential. When you take the differential of this constant term with respect to c, it becomes 0. So this term will be anyway 0. So we'll be left with this term and this term. Interestingly, Fy is not a function of C. For Fy, there is no C inside. So this will be treated like a constant in this kind of differential when you are differentiating with respect to C. The idea is we are minimizing the function for a given center C. So C is our variable. That's why we are differentiating C if this is not so clear. And again, we are saying that Bx here is C itself. So when we differentiate C with C, we get a constant. This value will become 1. And you are left with this fx bx, which is nothing but c minus y, because bx is also c and x is also c. So you are left with this function c minus y only. So effectively, the first term will converge to something like c minus y. This will be 1, the constant fy. And you have to find the values at limits minus infinite to c. So this will be 1. What about the second term? Let's examine this. Now here, the limits are minus infinite. So a is minus infinite to c. We are differentiating with respect to c, and the function is c minus y. This fy will be constant fy dy. So when I differentiate with respect to c, I get 1. We'll leave that for some time now, but we have understood that this will be integral minus infinite to c and differentiating del by del c minus y dy. So this is what we are left with after applying this Leibniz rule. So we get this expression. Let's examine this. That's why I did not move forward. I wanted to examine this in more detail. So let's look at the first term. When y equal to c, the upper limit, this becomes 0, right? And recall this fy is nothing but probability density function. So if y equal to minus infinite, at minus infinity, this again, this function will take a value of 0. At minus infinity, a probability density function would behave something like this. So extreme infinite, it will be 0. So this term is fully eliminated. Now let's come back to this. So this term is 0. Let's come back to this. Here, differential of this, like I was saying earlier, this will become 1. So it is nothing but integral of minus infinite to c probability density dy. And this is nothing but cumulative probability minus infinite to c, which is fc itself. The other limit will become 0 because at minus infinite, the value will be 0. Like I said earlier, at minus infinite, there'll be nothing, sort of no probability is there, 0. And the cumulative function at, if you look at the behavior of cumulative probability function, it behaves like this S-shaped kind of function where lower limit is 0. If you look at infinitely on this side 0 and upper limit will be 1. So here it is minus in c to minus infinity. This integral will be fc. In a very identical fashion, the part 2 of this differential, which is this, can also be solved. For example, again, the first term will become 0. If you look at this term, this expression is minus 1. So the only difference here is that differential of earlier was 1, of this term was 1. This term will be minus 1. So you'll have outside minus 1 integrated from c to infinity. Now, you know that when you integrate the right side, this is nothing. If this is fc, cumulative probability fc up till point c, then this is 1 minus fc. So when I integrate this function from c to infinity, essentially what I'm doing, earlier I integrated the left side of it, which was cumulative probability fc. Now I'm integrating c to infinite, which will be nothing but 1 minus fc. So this becomes 1 minus fc multiplied by minus 1. And therefore my overall resulting expression becomes fc minus into 1 minus fc equal to 0. Solving for this, we get 1 by 2. And this is the minimization problem from this approach, minimization problem for a solution to median. The solution will remain same if you use this check function, where the main changes, earlier we have used the weight as same as 1 by 2, but now you are using asymmetrically weighted error terms. Asymmetrically weighted error terms with their magnitude. So we are multiplying asymmetric weights to magnitude of errors. And when you integrate this kind of function will result, which looks daunting, but the solution will be same. Solution you'll obtain the quantile itself. So we'll not go through the full detailed proof, but when we optimize this problem, the solution, which is this, it is nothing but extension of what we already saw with the median. With other quantiles, the expression will converge to this, and finally this expression will come to here, 1 minus theta into fc minus theta into 1 minus fc, and the solving for this, you get fc as theta. So the center becomes q theta or quantile itself. So basically, the solution to this minimization problem of this expectation with check loss function becomes a generic quantile. For median it was half, and for any generic quantile position theta, it becomes q theta, quantile itself, the quantile value itself. To summarize, in this video, we discussed a simple proof of quantile regression model taken as a univariate quantile, a variable, simple random continuous variable y taken as a univariate quantile. And when we optimize the check loss function for a particular center, the solution we got was quantile itself, and for median we got the value half, which means for the center we got median quantile itself, 50 percentile. In this video, we'll extend our understanding of simple regression model, which was minimization of residual sum of squares, to quantile regression setting. We'll take the example of simple regression and extend it to quantile regression. So let us extend our logic of regression setting here. In a typical regression setting of y equal to beta 1 plus beta 2 x, y is your response or dependent variable, where x is your independent variable. Now here can be more than one variable like x1, x2 and so on. Then earlier we discussed unconditional univariate variables. Now they are replaced, though that unconditional mean of y is replaced with the conditional mean as follows. So you have minimization of expected value of y minus, this is your model. In this case, it would be beta 1 plus beta 2 x. So that conditional, so this is your typical conditional mean, and these deviations are your residuals. So earlier we had y minus the unconditional mean. We have replaced that with the conditional mean, which is this mu I comma beta. This is conditional to values of x, and sum of squares. You minimize the expectation of these residual squares to get your desired parameters in case of OLS. Here, this represents that conditional mean function, which can be a multiple of covariates xi and their multiplication with coefficient beta. So you can think of these xi and beta in vector notation form, where you can have more than one variables like x1, x2 and so on, and their corresponding coefficients betas, beta 1, beta 2 and so on. So this is your typical simple least square regression model setting. Now you extend the same approach for the quantile regression, but only in the case of quantile regression, you replace that least square minimization scheme with this check function. Recall we have detailed discussion about this check or loss function in case of quantile regression. And now instead of this conditional mean, you have conditional quantiles. So this q theta x would represent conditional quantiles, which means for each quantile you would have different parameter estimates of beta. So we can further write it in more appropriate manner as beta cap theta, which is obtained by argument minimizing argmin, which means minimizing expectation of this function. This is check of error. Now earlier we have this centroid as some kind of median or unconditional quantile. So we have this C as unconditional sort of quantile. Now we are replacing it with conditional quantile. So we have x beta and the deviation y minus x beta. You can think of x and beta in a vector form. So x can be a vector of x1, x2 and so on, and beta can be a vector of coefficient as beta 1, beta 2. So you have x beta matrix, which is your conditional quantile function, and this is when supplied, this error y minus x beta, these errors when they are supplied to this check function or loss function for quantile regression, you get estimates of beta that are quantile specific. So these beta estimates are quantile specific. For each quantile, theta equal to maybe 25 percentile or 50 percentile, which is median, or 5 percentile, you get different estimates. So this indicating that the parameters corresponding to each estimators are quantile specific. And recall here, as per this check or loss function, the negative errors were multiplied with 1 minus theta. So the magnitude of negative errors was multiplied with 1 minus theta, and positive errors was multiplied by theta. So you minimize this scheme, and when you minimize this scheme, you get the quantile specific coefficients or estimates. So essentially what we have discussed here is that this quantile regression setting is an extension of that classical estimation of conditional mean model. In conditional mean model, we had regression. Here we have conditional quantile function. So when we extend this quantile regression extension, we get what we call as conditional quantile functions. In the framework of linear regression, the QR model, the quantile regression model, is specific to a quantile, and it is formulated like this: q theta y x, which is quantile expectation, which is quantile specific value of y for a given x. So it allows y and x relationship to be quantile specific, allows that across different quantiles the impact of x on y is different and can be captured by this quantile regression function or quantile function, which is x beta theta, which means there is a vector of variable x and there is a vector of estimates beta. Now the beta is changing across theta. It's not constant. It's changing across quantiles where theta is from 0 to 1. Quantiles vary from 0 to 1. So this q theta is the conditional quantile function. I repeat, this q theta is a conditional quantile function which represents the relationship or impact of x on y, which is quantile specific, captured by this parameter estimates which are changing with quantiles. Now, the parameter estimated here, these betas in the QR model also have the similar interpretation as that any linear model like we have in OLS, like rate of change. So, for example, in regression, we said beta is partial del y by del x. Similarly, here also we have beta is nothing but partial differential of y with respect to xi for each quantile. So it is specific to quantile. So for each quantile, when you get a particular, let's say, estimate beta 1 theta for a quantile theta for variable x1, this would mean, for example, y1 and x, the relationship between y1 x1 at quantile theta is governed by beta 1 theta. So you would say that partial differential of y1 in a given specific quantile theta with respect to x1 is beta 1 theta. So beta 1 theta is the change in variable y per unit change in the regressor xi captured by beta I theta. So it remains that rate of change interpretation. So that rate of change interpretation retains similar to regression, only that now it is quantile specific. So now it is quantile specific as well. Earlier it was across all the entire distribution, it was same because it was representing the mean, but now because it is representing that particular quantile specific coefficient, it is for the thetath quantile, but that rate of change remains still. Visually, earlier what we were doing, we were looking at error terms. For example, if this is your value of yi and this was your estimated through conditional mean approach, then you would have done this square. So you were minimizing the square of this thing, this error term. So this error, whatever this error is, we were minimizing the summation of these squares. Now we are minimizing the magnitude. So now we are minimizing the magnitude of these errors to get the median. And if you want other quantiles, you multiply them asymmetrically. For example, 1 minus tau with negative error terms and tau with positive error terms. You multiply with their magnitude, and that is why we are calling it asymmetrically weighted error terms. We get different quantile specific coefficient. But if you want median, you simply sum up the absolute error terms. So this is typical visualization scheme. So to summarize this video, we discussed how to extend our understanding of simple least square regression model to the quantile regression setting. We noted there are a lot of similarities in terms of parameter interpretation across least square regression model, which was driven by means, as compared to this model, which is driven by conditional quantiles. One key difference here is that the estimates that are obtained are quantile specific. So the estimates of beta that you obtain are specific to given quantiles. But still, they measure rate of change in variable y for a given changes in values of x across different quantiles. In this video, we'll see how to optimize our quantile regression problem in the form of a linear programming problem in the form of a simple bivariate expression. Think of a simple two variable problem as y equal to beta naught plus beta 1 x1. This kind of problem, when estimated in the form of quantile regression, can be simplified or put as a solution to the following minimization problem. Here, we are trying to minimize this, and you can think of this as that residual or error term from the model. This residual, because we are taking magnitude of it, we are trying to minimize the summation of it. This will give us the median. So this is median estimation problem, and it can be transformed to an equivalent linear programming problem. Let's see how. So here, if we, instead of the original function, this one, if we minimize some kind of residual ei, we'll describe this residual. If we minimize the summation of these residuals, and we describe these residuals as follows with two conditions: one, greater than this error term and greater than its negative value. So if it is positive, then this. If it is negative, then this. Effectively, here ei is the auxiliary variable representing error at the ith point. And these two conditions effectively transform this as a error which is greater than both positive and negative sign converted to positive with this, which effectively means we are putting our ei such that it is greater than the magnitude of the error. So this is typically, this expression will ensure, these two expressions will ensure that it is greater than the max of both, which means magnitude. So when it is positive, then greater than, and when it is negative, then magnitude with a minus sign. Now, the problem is a little heavy and complex. It can be further simplified a lot with putting one additional constraint that ei should be greater than equal to 0. This means that ei's are taken to be as positive only. So all the negative ei's will be eliminated and effectively the computation will be much more simpler. So from the consideration set where optimization goes on, the negative ei's will be eliminated because it cannot be any way, the solution cannot be negative because we are using magnitudes. Now, the previous solution set that we discussed with this, that was effectively for median. This can be transformed by using weighted sum of residuals. When we minimize the weighted sum of residuals, we effectively get a quantile. So we multiply the positive residual magnitudes. So those EIs, the positive ones with P and negative ones with 1 minus P, where P represents the quantile. So the pth quantile regression estimators, beta P naught and beta P1, can be obtained with this scheme rather than the earlier scheme. We multiply P with the summation of this positive residuals and 1 minus p with the summation when the residuals are negative, but although the multiplication is with the magnitude. So in that case, we use this kind of scheme where here we, instead of this, we will be using those error terms that we have defined earlier. So these error terms will be multiplied. To summarize, in this video, we discuss how to transform the quantile regression problem in the form of a linear optimization schedule with certain transformations which lead to less computational burden. In the previous video, we have understood the linear programming problem or linear optimization of quantile regression. In this video, we'll apply that with the help of a simple example. Think of a typical two variable problem where you have a regressor variable horsepower, which is given here for 8 observations, and the price, again 8 observations, as the response variable for 8 cars. And we want to run a typical regression model like price equal to beta naught plus beta 1 into HP with error term. Now, here we can model these error terms in very simple fashion. For example, let's look at this first expression. For that, you have beta naught plus 63 into beta 1 minus 7.4 is the positive error. So error should be greater than this. And at the same time, error should also be greater than equal to minus of this beta naught plus 63 into beta 1 minus 7.4, which is nothing but this expression. Similarly, for the second expression, we can have beta naught plus 127 into beta 1 minus 10.1. ei should be greater than this, and also ei should be greater than equal to minus of this, which is beta naught plus 127 into beta 1 minus 10.1. So in this fashion, we can keep writing equations. So if there are 8 observations, 1, 2, 3, 4, 5, 6, 7, 8. So there will be 16 such expressions, and we'll minimize the residual here, this summation I equal to 1 to n, where n is 8. We'll minimize this expression, and also we'll add one more condition in addition to the 8 formations that we have seen earlier. In fact, it is 8 into 2. We'll also add one more, which is ei should be greater than 0. Now, you notice that here the multiplication is, there's no weighted multiplication, which means effectively we are multiplying with the same 0.5. And the solution to this minimization problem will result in the median quantile, 50th percentile, and the values are shown here. It will result in this kind of straight line where the intercept would be minus 0.6 and beta 1 is 0.13. So the relationship is price equal to minus 0.6 plus 0.13 into HP. So this was a rather simple quantile regression problem for a median solution. We were looking at median solution. We look at 8 data points. We formulated 17 equations or conditions, and we minimized our objective function, which was summation of I equal to 1 to n. This summation was minimized with these conditions, and we could obtain the median solution or the median of 50th percentile or median quantile. In the previous video, we have understood the quantile regression with two variables, one independent, one dependent. Now let us understand with the p dependent independent variable problem. The typical model for a linear quantile regression appears like this: y equal to x beta theta plus epsilon. Here y with n observation is a vector of responses, so there will be n responses, and x is a regressor. If there are p variables, then it is sort of matrix kind of thing, x1p, x2p, and so on. So you'll have p regressors, and each regressor x1, x2 up till xp, and each regressor will have x1 dash, x1 double dash, and so on. You'll have n observations corresponding to each regressor. Because you have p regressors, you'll have a matrix of p cross n. In terms of coefficients, you'll have quantile specific coefficients. For example, because this relationship is now quantile specific, we are estimating quantile regression only. So beta p theta will represent those p parameter estimates for p regressors x1. So for example, you'll have x1, x2 up till xp. For each you have beta 1, beta 2 up till beta p, and all of these are quantile specific. So beta 1 theta, beta 2 theta, and so on up till beta p theta. So all these coefficients are quantile specific. And then lastly, you have error terms, which are the vector of unknown errors, and these are specific to a quantile. Now, when we are estimating the median estimate, for that we are minimizing the least absolute summation of this for estimating beta, which is corresponding to conditional median. So it is the solution to the following minimization problem. Here we are minimizing the error terms, its absolute value summations. So the least absolute estimates, their summation is minimized. The same least absolute estimation for median can be transformed to that check or loss function rho theta, where the magnitude of each of the error is multiplied with 1 minus theta for negative errors and theta with positive errors. So you'll have, instead of that function, you'll have this check function. And when this is minimized, the solution to this optimization problem will be those betas for that particular quantile theta. To summarize, in this video, we transformed our two variable quantile regression problem into a p variable, p dependent, independent variable, and a dependent variable problem. So a linear regression model with a p independent variables. In this video, we'll understand the quantile regression application with the help of a simple example and the application of a single dummy regressor in the model. Let us set the background here. So we have in our data the returns of two variable. It's a sort of data where you have HDFC return, which is a large cap, and small cap, which is IDFC. Now we want to summarize these returns with the help of their size variable. So size is our sort of nominal, or you can call it a dummy variable. What is a dummy variable? It takes a value for 0 for the small stock, which is IDFC, and 1 for the large stock, which is HDFC. And we want to estimate this kind of model where return is regressed on the size variable, size dummy. What will happen? When we run this kind of typical regression model with the OLS scheme, OLS will provide the mean. For example, the beta naught will be the mean of IDFC variable, which will represent when size variable is 0, size is 0, and it will represent the mean return of IDFC. When size is 1, the value beta naught hat plus beta 1 hat will represent the mean return of HDFC. So effectively, beta 1 hat is whether significant, statistically significant or not. It represents the difference, whether that is statistically significant or not, between IDFC and HDFC. So effectively, the results are very similar to two sample t-tests, where you get to see the mean of one variable, IDFC returns, as beta naught hat, mean of HDFC returns as beta naught plus beta 1 hat, and their difference, which is beta 1 hat. In a similar manner, we can estimate the quantile regression problem, which is written like this. But now the problem for each estimates of beta, they are quantile specific to a quantile theta. So when you are running this kind of regression model, you will get beta naught theta, which will give the theta quantile value for IDFC, the theta quantile for IDFC return, which is beta naught theta. For example, for mean, that is theta equal to 50 percentile, you'll get, median, you'll get the median return for IDFC, which is beta naught. Similarly, for median, that is theta equal to 50 percentile, you'll get the median return for HDFC, which is beta naught hat plus beta 1 hat, and their difference is beta 1 hat. Similarly, by varying theta from 0 to 1, you can estimate or generate the full spectrum of quantiles for both the IDFC and HDFC. Before you run the regression, it would be good to visualize these returns. For example, box plot, where you can see these whiskers represent the extreme returns. So the center line is the median. This is your 75 percentile. This is 25 percentile. These whiskers are sort of interquartile ranges beyond the 75 percentile, 1.5 times IQR above and 1.5 times IQR below. And these dots are sort of extremities. As you can see here, this IDFC has more extreme returns, but we'll examine this in more detail. Again, if you look at the density plot here, density plot also shows that the green curve has more extreme tails upper here. So this confirms our box plot. This is the density plot of IDFC versus HDFC. IDFC is in green, so we can see here more extreme tails in the tails. Similarly, in quantile plot also, we can see the green one. IDFC has more extremities around the tails. The last one is the comparison of quantile of IDFC and HDFC. We can see they are not similar. So if they were on the straight line, they would have been similar, but because they are deviating from the straight line, it appears there is asymmetry. Particularly IDFC is higher on the positive side and lower on the negative side. So now let's run the empirical results. Our OLS estimates from the model are shown here. So this beta naught is the mean return of IDFC and beta 1 is negative. This is a difference. So when we sum them up, 0.168 plus 0.156, this would be the mean return of HDFC, which is much smaller than IDFC in fact. So these are the mean estimates. And in fact, the difference between IDFC and HDFC mean return is quite high, which is represented by beta 1 hat. What about conditional quantile? So we run these regressions for 10, 25, 50, which is median, 75, which is third quantile. You can call it as Q3. This is Q2. This is Q2. This is Q1. So this is median. And this is 90th percentile. You can see this beta knots represent the corresponding quantile values for IDFC. So this is for IDFC. For example, minus 3.1% at 10 percentile, minus 1.5% at 25th. Median is 9 percentile, 9%, and 90th percentile is 3.39%. The difference between the medians of IDFC and HDFC is this. So if I add this with this, which will become minus 2.01, this is your quantile value for HDFC for the corresponding quantile. Similarly, if I add this and this will become my corresponding quantile value for HDFC as per quantile regression. So these are the quantile values as per the quantile regression, and the same values, if I, without running this regression, if I put them separately and separately apply the quantile function, every R, Python, all these have these tools, you can apply quantile package and break them into 10, 25 and so on. So when I break them using this quantile function, sort of unconditional, what you call as unconditional quantile. These were conditional quantiles because we were running them conditional to the size variable, but now we are running them separately unconditionally and we get a very similar result, which means our experiment was true. We are getting these quantile values only with the help of quantile regression. So this nominal size variable gave us a very important or useful way to generate quantiles of these variables when they were mixed, when they were conditional. Unconditionally, one can also segregate, but even if they were given together with this size variable, dummy size 0 for IDFC and 1 for HDFC, gave us a very unique way to extract the quantiles of these two returns, IDFC and HDFC. To summarize, in this video, we compared and contrasted the output of OLS regression and quantile regression, and we also saw how to interpret the quantile regression model with the application of dummy variable across different conditional quantiles. In this video, we'll add more categorical or nominal variable to increase the complexity of exercise interpretation in the QR model. Let's revert back to our original return data and say we wanted to understand the seasonality or cyclicity of the data. So we divide into 4 half-yearly periods, and when you divide into 4 half-yearly periods from Jan to June 21, July to Dec 21, Jan to June 22, and July to Dec 22. Now, as per the dummy variable rule, if you want 4 periods, 4 categories, you add n-1 dummies. That means 3 dummies. So we add 3 dummies, namely period 2, 3, and 4. By default, the unloaded dummy or the dummy that is not explicitly mentioned will be loaded in the intercept. So first, we run the OLS estimate, and like we said, beta naught will become our reference category for the first period, which is not explicitly included. And let's say we obtain these results. The idea is to interpret is like this. First, the unloaded category that becomes reference category, which is beta naught, which is 0.133. So these are our returns in the first period. Now, subsequently, if you want to know the second period return, you need to add its coefficient to the reference category. That means period 2 return, this beta 1 value of minus 0.054 to be added to beta naught, this combined will be your period 2 return. Similarly, if you add this to beta 2, you'll get period 3 return, and add this to beta naught, you'll get period 3 return. So this is your reference category, and subsequently these are the differences from each period 2 this, so this becomes beta 1 is like period 2 minus period 1, beta 2 is this is period 3 minus period 1, this is beta 3 is period 4 minus period 1. So this is how you interpret the results. So to simplify things, when period 2 dummy takes a value of 1 and all the other values are 0, then, so for example, when all the values are 0, then you get the regression as beta naught theta. This is your reference category period 1. Similarly, when period 2 takes a value of 1 and this becomes 1, others are 0, so your resulting value beta naught plus beta 1 becomes written for period 2, and so on. And this is quantile specific now. So when we are running in quantile regression form, these coefficients are quantile specific, but other than the dummy variable interpretation of adding the dummies, the reference category, and adding the corresponding dummies, for example, beta naught plus beta 3 is for the period 4 return, that procedure remains similar for OLS, whether it is OLS or quantile. So for example, we obtained these results for quantile 10 percentile, 25, 50, 75, 90. Notice beta naught, the reference category is minus 2.72, which is for the period 1 result for 10 percentile. So all these results, so beta naught for 25, 20, 75 and so on, these are for period 1 returns for respective quantiles. Now let's suppose you want for period 2 for a particular quantile, let's say 10 percentile. So in that case, you have to add this minus 2.72 to this one and you'll get this. Similarly, for period 2, 25 percentile or Q1 is this, median Q3 and 90. Similarly, for if you want for period 3, you have to add this reference category to beta 2 to get P3 for each of the quantiles. Similarly, if you add reference category to beta 3, you'll get for the final. So you can get conditional quantiles like this. Now, just to prove a point, I have also calculated unconditional quantiles. That means without running the regression, I have simply extracted P1, P2, P3, P4 separately and computed their respective quantiles. And you can see they are very similar. So unconditional quantiles and with mixed data using dummy or nominal variables for each category and minus one categories, we also get similar results, which prove the point that quantile regression is effective in its use. To summarize, in this video, we increased the complexity of exercise. We added more categories and analyzed 4 period returns across different quantiles. We compared the conditional quantiles with the category period variable along with unconditional quantiles. By examining these returns separately across periods, we obtained very similar results, which confirmed the utility of quantile regression. In this video, we'll add a quantitative regressor to the quantile regression model and understand its implications. As a typical example in finance, we'll use the relationship between volume and return and volume and volatility with the help of quantile regression. Here we are regressing volume, in fact log of volume on return and log of volume on volatility. Now volatility is nothing but return square here. So basically the idea here is that when you run this regression through OLS approach, you are getting the mean estimate of these estimates beta naught, beta 1. However, the relationship between volume and return volatility, as we'll see shortly, may differ across different quantiles. Different quantiles, that is maybe Q1 lower quantiles, Q1, Q and mid quantiles, Q2 upper quantiles like Q3. The relationship may change, as we'll see shortly. And for that, OLS is not very well capable, and we need a sort of quantile regression approach for that. Let's first examine the volume across its quantiles. As we can see, the volume of IDFC is more scattered here, while HDFC appears to be like this. So there's a difference. If you look at quantile regression here, I've simply visualized the quantile regression slope. So you can see across upper quantiles, the light blue, and dark blue across lower quantiles, the relationship slope also between return and volume is different. So across quantiles, the relationship between log of volume and return is different. So that is another intuition. Similarly, for log of volume and volatility, also the slopes are different across different quantiles. So when I run the quantile regression and beta naught is the intercept, more importantly, our focus will be on coefficient let between return and log volume and volatility and volume. Notice for OLS, the mean value is 0.65, but when you look at across quantiles 10, 25 percentile, median 75 percentile, 90 percentile, it starts from negative as we saw in the graph and turns positive. Recall the graph, return this negative to positive. Similarly, Between volatility and volume also, there is a drastic change in the slope. While the mean slope gives us some kind of average picture, but across quantiles, the relationship is very different, which again solidifies our claim that the relationship across different quantiles between volume and return varies. So there is a conditional shape across quantiles between the covariate volume and return. Let us finally visualize the relationship. And here you can see return versus volume. Intercept, will not focus on intercept. Look at the slope coefficient. So it starts from here minus 1.5 and it increases positive. As we move towards higher quantile, the relationship becomes more and more positive. Similarly, for volatility and volume, as you can see, it starts from close to zero and becomes more and more positive as we move at the higher quantiles. We are not exactly sort of looking at the theoretical underpinnings behind it. For example, here you can conclude when you are looking at a higher quantiles of volatility, you would understand that when information arrives, there's a high volume and high volatility with information arrival. So there's a higher relationship. So you can put some kind of theoretical underpinning, but that is not the objective here. The idea here is to show that across the quantiles, the relationship is not homogeneous. There's a heterogeneity in relationship and the typical OS approach, which gives you the mean. So this dotted line would give you the mean values. This dot is for the mean values. You can see the constant homogeneous mean solution is not the correct one, given so much variety in the actual values. So therefore, quantile regression is more capable to handle such heterogeneous relationships. To summarize, we added a quantile regression, which is volume in the model, and its relationship between return and volatility we examined. We found that the relationship is not homogeneous like what OLS would have us believe, but in fact it is very heterogeneous and varies across quantiles. So a conditional quantile approach with quantile regression is more capable to estimate and examine such relationships. Let us summarize this lesson. When describing the response of fixed values of predictor variables, the conditional mean model cannot be readily extended to non-central locations. For example, behavior of lower tail versus upper tail, for example, rich versus poor people, may exhibit very different characteristics. Thus, the focus has shifted to non-central locations such as quantiles. The homoscedasticity assumption frequently fails, for example, issues such as heteroscedasticity, and focusing exclusively on central tendencies can fail to capture informative trends in response distribution. Heavy tail distributions commonly occur in the financial markets data, leading to a preponderance of outliers. The conditional mean can then become an inappropriate and misleading measure of central location because it is heavily influenced by outliers. Quantile regression models can be easily fit by minimizing a generalized measure of distance using algorithms based on linear programming. While classical regression gives only information about the conditional expectation, quantile regression extends the viewpoint on the whole conditional distribution of the response variable. The mean and the quantiles are particular centers of a distribution, minimizing a squared sum of deviations and a weighted absolute sum of deviations respectively. This idea is easily generalized to the regression setting in order to estimate conditional mean and conditional quantiles. A simple linear regression model with a quantitative response variable and a dummy regressor allows us to compare the mean, that is in classical regression, and the quantiles, that is quantile regression, between the two groups determined by the dummy regressor. Using a nominal regression, such a comparison is among the G groups corresponding to the G levels of the nominal variable. For quantile regression as well as for classical regression, the parameter estimates in the linear models are interpretable as rates of change. The beta I theta coefficient can be interpreted as the rate of change of the theta quantile of the dependent variable distribution per unit change in the value of the ith regressor. Least square estimation of mean regression models ask the following question: how does the conditional mean of y depend on the covariates x? Quantile regression asks this question at each quantile of the conditional distribution, enabling one to obtain a more complete description of how the conditional distribution of y depends on x.